we need to finish the notes for section 2.5, and then I'm going to see what happens next. But we left off with an example. And I'll put up a few parts of the example, but the next thing to do is show that that function is continuous on its domain. And I will try to grade your exams tonight. We'll see how that goes. Notes. Okay, we had f of x equal to the root of 16 minus x squared. Just to be sure, is this recording the right way for you to read it correctly? Or is it supposed to be flipped? So someone let me know. Does this look backwards?
No, it's fine.
Okay, cool. Thank you. All right, we found the domain. It was the interval that goes from -4 to 4. Okay, and the problem asked for us to show that the function is continuous on its domain, and for this set, we need to do it in two parts. The first part is to show it's continuous from the open interval that goes from -4 to 4, and then we have to show it's continuous at both of the endpoints, this side -4 and that side +4. Let's see. Okay. We are going to put some elements in that set. We're going to let A exist in the set that goes from -4 to 4. And remember, this is a symbol that means like element of or exists in. And then the set that goes from -4 to 4, but doesn't include either end. Okay, to show that the function is continuous on that interval, we need to show that the limit as x goes to a of f of x equals f of a. I'm going to start with this side and just work through it and then make sure that it is equal to f of a, whatever you get if you just put a into your function f. I don't think so. Okay, so we're putting a function in, so it's the limit as x goes to a of the root of 16 minus x squared. Okay. This would be the power rule. We're going to bring the limit underneath that root, or I guess it's a root rule. I was thinking of it like a 1/2 power. Either way, underneath the square root, we'll take the limit of that function, or that part of the function, 16 minus x squared. I was going to try to mention this yesterday, but it's okay. I'll just kind of have to maybe make it a note in the test while I grade. But I don't know if I've made it clear that until you actually let that x value go to that number a, if you haven't actually have thought about having your value approach the number yet, and you've just been playing with the function, you need to keep this notation on the side. So you need to keep the limit until you actually let let x go to the number. Anyway, so we need to continue to have this limit on the side as x goes to a of this part. And then we're just gonna put a in here since this is a polynomial, still underneath the square root. So now I am letting x go to a. So my teacher would sometimes draw a little arrow, like now I'm gonna have this x go to a, and I can drop the limit part, and I'll take the root of 16 minus a squared. And this would be what you would get if you just plug a into your function. You'd get out the root of 16 minus a squared. So this is equal to f of a. Which is what we were trying to show. So just to be clear, let's say you started with f of a, it means put a into that function f, and you would get this, the root of 16 minus a squared. Okay, so we've shown that the function is continuous on that open interval. Next part you have to do with these types of problems, and if you're going to continue on the math journey and take something like Math 130 A and B, you'll be doing problems like this where you do the open interval, and then you have to check both endpoints. So I have to check the end for -4, and we have to check the other side with +4, and then we'll be done. Okay, first one is to show that the limit as x goes to -4 from the right, which a picture is going to help. We'll draw a picture. From the right of f of x is f of -4. Okay, first picture. The domain is a set from -4 to 4. And we've already shown it's continuous, on this part right here. The function is continuous on the open interval from -4 to 4. Now we're checking this end. So we're going to -4 from the right. So I'm going to show, this is like number 2, part A, is the limit as x goes to -4 from the right. Of your function f of x would be equal to, we want it to be equal to f of -4, and that way it would be continuous. Let's get started. We're going to start here with the limit. The limit as x goes to -4 from the right of your function. No, who's getting this? Didn't get limit. It's root of 16 minus x squared. And again, I brought the limit under the root. And I haven't taken the limit, haven't had x actually approach -4 yet, so I need to keep this limit part under that root. Okay, so we're here. This is what I'm trying to show over here, just keeping it as a little post-it of like what I need to do. From this step, I will let x go to -4 from the right. And when that happens, I can stop writing the limit notation. And I like to draw a little arrow over the variable and write what it's going to. So x is going to -4. So I have the root of 16 minus -4 squared. So it's the root of 0, which is 0. And that's what you would get if you put -4 into the function. You get that 0. Okay. That side equal to that part. And we've shown that f is continuous at that end, where x is equal to -4. Okay, and then the other part of the next step, step 2, is to show it's continuous at the end that has +4. Let's see, I'm gonna draw the picture again.
Is that number 3, by the way? Is that number 3, by
I
the
would
way?
say I call it more like part 2, like number 2, part B. Like that's part A. It's continuous at x equals -4. It's like part A. Number 2, part A. And this would be like next, number 2, part B. Okay. Sure. I need a picture really quick to think about what we need to show. So we want to get f to be, or we're trying to prove that f is continuous on its domain. The domain goes from -4 to +4. We did the open interval, this part. We did this side, check. We're doing this side now. And we need to go to 4 this way. Sometimes it's important, like the direction you're going to your endpoint at, like this one's not too bad. This function's not crazy, but still. We're trying to approach +4 from the left. I'm trying to get the limit as x goes to 4, +4, from the left. Of f of x equal to f of 4. Okay, so I wanted to mention that like in most math problems where you need to show one side was equal to the other side, you can't really work with both sides at the same time. You need to pick one side and manipulate it into being equal to that other side. And you usually want to pick like the messier side. So this is why I would pick this messier piece, the limit of the function, take that limit, play with it, and get it equal to f of that number. But I don't want to ramble on. Okay, let's just take the limit. The limit as x goes to +4 from the left. Okay, so it's the limit as x goes to 4 from the left of the root of 16 minus x squared. Bring the limit under the root. Take the root of the limit as x goes to 4 from the left of 16 minus x squared. Okay, so when you're taking a limit of a polynomial, you can just put that number in, putting in a 4 for x. And once I do let x go to 4, like this x right here, I don't need the limit notation after that. We have the root of 16 subtract 4 squared. So it's another root of 0, which is 0. Which is what you would get if you put 0 into your function, which is f of 0. Not 0 into the function. If you put 4 into the function, you'd get out 0. So f of 4 is equal to 0. So we showed what we needed to show, which means f is continuous at the other end where x is equal to 4. Which means it's continuous on its domain. The whole interval that we found. So first summarizing what we just did. F is continuous at x equals 4. So once you take that part where we showed is continuous on the open interval from -4 to 4, along with the ends, -4 and 4, after all of that being checked off, you can say f is continuous on that interval that goes from -4 over to 4. And again, like just to remind some students, like the square bracket means you can't include that number. So the set that includes -4 and goes over to 4 and includes that end. Oof. Okay, something new. So we're
Wait,
gonna
are
do.
we done with this question or still doing it?
Nope, we finished. Yeah, that's what we were trying to do. Show that it's continuous. All right, so you're gonna have a list of results. So for two functions, f and g. Put f of x, like f is a function of x. And g of x. G is the function, its inputs are x. Okay, and both of these functions are continuous at x equals a. Hi everyone, looks like we're still recording. Just a side note, since we all moved back to face-to-face instruction, the hotspots were like removed or like canceled. And so I had to request to have the hotspot I was given reconnected. So right now I'm using my own internet, which is not the best. So hopefully we'll make it through the meeting without losing each other again. If we lose each other a few times, we could just call it a day, but let's see what happens. All right, I have my two functions f and g. They're both continuous at x equals a, and I need a number c. Let c be a constant, so c is some real number. Okay, then the following functions are continuous. Okay, so f is continuous. If you multiply that by a number, it's still continuous. So c times f of x is continuous. If you take a continuous function and add or subtract it to another continuous function, that would be continuous. If you multiply two continuous functions, it's going to give you a continuous function. And the last one has a little exception where if you have two continuous functions and you take that continuous function f and divide it by g, that's continuous except at places where g of x would equal 0. So this is 1. Number 4, we could take f of x divided by g of x. And that would be, and they're both continuous functions. So this is a continuous function except at places where g of x would equal 0. I guess you'd say except at values of x that make g of x 0. Trying to get us to the end of this section. So this part I'm just going to read over. I was going to skip it, but I could just at least tell you some functions that are continuous on their domains. So we mentioned polynomials. Rational functions are continuous on their domains except at the places that make the denominator 0. Also, trig functions are continuous functions like the sine function and the cosine function. And the tangent function.
Wait, that's all. Hello?
Yeah.
My bad. Wait, the at values of x that make g x equals 0, that's for the quotient one, right?
Yeah, for number 4.
Okay, just want to make sure. Thank you.
Yeah. Okay. Also, some more, just a quick little wrap up of some functions that are continuous, but really whatever function you get in the future, you're going to have to just check it either way. So exponential functions, logarithmic functions, and root functions. Yeah. Okay. Let's move on. We are going to go over the composition of functions. Okay, first a reminder about notation. F of g of x. So this is f, this is a small circle of, and then your function g, and then close that, then of x is also written as, so f, and then of g of x, close. Okay. And we're going to just do a quick little example of taking we're going to call this h of x. It's ln of 9 minus x squared. Okay, so the outer function f would be ln of x, and the inner function g is this 9 minus x squared. So like the inside function, like this part, g of x, is this part here. And then the outside function f is that part there, ln of whatever you put inside, which we're putting inside this function. Okay, and we have a theorem. If f is continuous at b, and the limit as x goes to a of g of x equals b, then the limit as x goes to a of f of g of x. Will be equal to f of b. Okay. I'm going to put an extra piece in here. So before we get to this part, we're going to do an extra little piece. Okay. We're going from here. The limit as x goes to a of f of g of x. We're going to bring the limit inside here. So take f of the limit as x goes to a of g of x. Okay, then you've got this limit as x goes to a of g of x equal to b. So we're putting a b right here, and you have f of b. Okay, and I only have like 2 minutes, but I'd like to do one example, and we'll come back next time and do like 2 more examples. Okay, we're gonna do the limit as x goes to 2. Of ln of 9 minus x squared. Okay, ln of x is continuous for x values that are greater than 0, just kind of curves over to the right. So we're having x go to 2, and I can bring that limit inside of the function and have ln of the limit as x goes to 2 of 9 minus x squared. Okay, this is just a polynomial, which means I can just put that number right in there and have x go to 2. And that means, and then once I have like taken the limit and then x approach that number, I don't need the limit notation anymore. And I just have ln of 9 minus 2 squared. Which is ln of 9. I think that's it for today. My goal really is to try to grade your exams, but if I can make homework for 2.5, I'll try, because we're almost to the end of this section. But we'll finish 2.5 next class. I'll see you tomorrow.